and then he put the magnet on it and then went down.
Right. Okay. Thomson's cathode ray tube. I've got an animation of that on Moodle, so you can all check that and see some pictures of that. With the cathode ray tube, he saw from the cathode to the anode this glowing beam of light, and he saw that when he brought a magnet or a positively charged plate near that beam of light, then the beam would start to bend toward it. That green's probably not showing up on camera at all, but the beam would bend toward positive, would bend away from negative. Because the beam of light would be bent toward the positive pole of a magnet, meant the beam must be what?
Negative.
Negatively charged. And JJ gave us the word electrons. Okay. Number 9, what was discovered about the rays in the cathode tube during Thomson's experiment? I think we just covered that.
Negatively charged.
Negatively charged, tiny particles. So the two questions are very similar. Number 10, what was discovered or determined in Millikan's experiment? What did Bobby do? Robert Millikan. The oil drop experiment. Okay, so Millikan was oil drop. And there's another nice animation or diagram of that on Moodle as well. Millikan, through the oil drop experiment, by stopping a drop from falling using the voltage across two charged plates, he was able to counteract gravity, use the charge to mass ratio to figure out the exact amount of charge. Now we refer to an electron as being -1. Okay? That's its relative charge compared to a proton or a neutron. And -1 is fine for our purposes, but there's an actual number, like 1.6 times 10 to the -19th or 10 to the 19th coulombs. Is it negative or positive 19? I forget. Okay, there's an actual value for electric charge as well. For our purposes, saying it's an electron's -1 because the proton's a +1 is perfectly fine.
So we found the exact charge of electrons?
Yes. Number 11. Ernie, what happened to the alpha particles in Rutherford's experiment? They hit the nucleus, and what did they do when they hit the nucleus? They ricocheted off, okay? Some good animations on Rutherford on there too. And in fact, if you go to your textbook website at my.hrw.com and log into your textbook, you can see all of the book animations for this chapter as well. And they give a nice diagram in motion of what the electrons are doing. So when Rutherford was shooting alpha particles at very thin layer of gold atoms, most of those particles were going where?
Straight through.
Straight through. So they weren't hitting anything. This is what we did with the marbles. And then sometimes they hit near something and were deflected a little bit. Okay? Maybe one hit near there was deflected. And sometimes they came in and kind of hit dead on in the center and were bounced backwards. That was thanks to Ernest Marsden, by the way. And from that he realized, well, there must be something else in that atom. There must be something small, must be dense, super mega dense, and it must be positively charged because alpha particles were pretty high energy. They are already positively charged. Alpha particles are helium nuclei with +2 charge. So if a positive charged thing came near something else that's positively charged, it's going to get deflected. Either knocked backwards or kind of off its track out of the way. Okay, are we good on Rutherford? Or? We did spend a decent amount of time on that lab and stuff. Alrighty, 14? Right?
12.
12. What conclusions did Rutherford make from the gold foil experiment? Well, how did he describe the atom? And again, in describing one answer, I described the other one as well. So he found the nucleus, realized that all of the positive was concentrated right in the middle instead of being spread out like Thomson thought it was. Right, so Thomson had a nice idea to start with, but Rutherford's experiment changed that explanation, built on it, added something new. You good? 13, similar to number 12. Okay. So, 3 questions about Rutherford's experiment. There is a simulation posted on Moodle as well that you might want to try. You can adjust things being shot and all that. 14, the mass and charge of a neutron, proton, and electron. So if I asked you, which of the elementary particles has an extremely low mass and a charge of -1, you would say an electron. And if I asked you, which subatomic particle has an extremely small mass and a charge of +1, you would say?
Proton.
No, you would not.
Nine.
None of them, because of the extremely small part. So they're going to be relative to each other. I know relative to humans, protons, neutrons, electrons are extremely small. But when we're talking about how protons, neutrons, electrons compare to each other, the protons and neutrons are about the same mass. And this question is going to be in terms of relative amounts. So we know electrons, -1 charge, a mass of 1/1837th, the mass of a hydrogen atom, protons +1 charge, relative mass of 1, neutrons, neutral, no charge, sorry, charge of 0, and a relative mass of 1. Okay, so this question is going to be in terms of relative mass. Okay. Alrighty, 15. How to describe the nucleus of an atom, the characteristics of the nucleus. If you had to describe the nucleus of an atom to, say, a 2nd grader, have they heard of atoms?
Yeah.
Kindergarten, you got to do scientific notation. Right, like for simple and fun. Okay, so if you had to describe the atom to a 2nd grader, our nucleus, what would you say? It's positive, yes. It's happy.
Made of
Those
protons and
and-
neutrons.
It's made of protons and neutrons. And what if they say, what are protons and neutrons?
Positively charged particles and no charge.
Positive particles with a positive charge and particles with no charge. And could we run through a nucleus if it was really big? No, because why?
Dense.
It's really dense. There's a lot of material packed really close together. Okay, and would a 2nd grader understand that?
No.
Do 10th and 11th graders understand that?